So in this last video on our series on the distance formula, we're going to talk a little bit about what you can do with the distance formula in more advanced settings and why people actually care about this kind of thing. It actually turns out that our distance formula, or really the Pythagorean theorem, so let's take a look at that again. Remember, the distance formula was this guy here, and it came from the Pythagorean theorem, which looks like this. These kinds of formulas can be used in lots of different places. In fact, a more important general question is just how do you compute distance at all, and what do you mean by that? Sometimes the distance that you're interested in might actually not follow that rule. For example, if you live in a city that has a gridded road system, so you have these like east-west roads and north-south roads, and you want to know how far you'd have to walk to go from here to say this point over here, well, you can't go in a straight line because there's no roads there. So instead, you'd have to walk through these two blocks and then walk through that block to get to that corner there. Measuring distances along sort of how far you'd have to go horizontally or vertically in order to get there, if those are the only types of moves you can do, is something called the taxi cab metric. You can kind of see why we call it that, since it's the distance that the taxi cab would have to follow in order to get there. So if you're interested in a real-world application of the distance between these 2 points, you might not be able to use the Pythagorean theorem, which would compute sort of that as the crow flies distance between those 2 points. You might have to use something else. So our distance formula may change depending on the setting that we're in. But this particular distance formula based on the Pythagorean theorem itself still has a huge amount of utility because it's how you compute distances in a flat space. For example, if you wanted to compute, say, the length of this curve, you're going to run into some problems because you can't just stick a measuring tape on here. It's not straight, so you can't use this directly. But what you can do is you can, let's say we wanted to measure the length of the curve from here to here. What you can do is you can break the curve up into smaller segments like this and approximate that curve by straight line segments at each of these points, and you get a pretty decent approximation of what the curve looks like. To find the length of each of these straight line distances, you use this formula or this one here, and then you add it up in order to get the full arc length, or at least an approximation of the arc length. This is where the calculus comes in. In order to make this exactly the arc length, what you have to do is make the width of each of these segments here go to 0, so that you're adding up sort of infinitesimally small pieces. And that's where you need the calculus for. As you do that, the differences here become derivative-like quantities, and then you're adding up something that's infinitesimally small. That ends up being like an integral. And so what you end up getting is an integral formula that looks like this. The length of this curve here, which we'll call L, will be equal to the integral from wherever you start to wherever you end. And then what goes in here is based off of this formula up here. But there's a little bit of a catch to it. It depends on how you write this curve out. If you write it as a regular function, y equals f of x, then the formula you're going to get here is 1 plus the derivative, which is that dy dx term, squared times dx. But it's not really exactly clear just from this formula why that's the right thing there. So it's a little easier to see if you parameterize this curve. So instead of using y equals f of x, what we'll do is I will give you a function that depends on t, and what it does is at each point t, it'll give me a coordinate. And in this coordinate, it'll give me an x coordinate at a certain time t and a y coordinate at a certain time t. So now I have an equation for this where the t coordinate is telling me sort of where I'm along, and I have to match up sort of these a, b's to whatever the x's and t's that are going to work there. So if this is, say, t equals 0 and this is t equals, I don't know, we'll say c or something like that, then what I'm saying is that x of 0 is equal to a and x of c is equal to b, and then the y's just sort of follow this thing here. And if I write the arc length formula using this, you can start to see where it comes from here. So don't worry too much if you don't know what the integral is. We're just talking about loosely where these things come from. This would end up equaling the integral from 0 to c of the square root of dx dt squared plus dy dt squared times dt on the outside. Now, this is a more interesting formula that looks a little more like that. You can see I've got a square root with the sum of two squared quantities. This here, this derivative, is comparing differences in x's to differences in t's. That's what the dx and the dt kind of stand for. This one here is measuring small differences in the y coordinate compared to small differences in the t coordinate. So again, I have these ratios, and then I'm multiplying by the t coordinate. What I'm really doing here is I'm adding up essentially these thin, super tiny distances. So if I get really, really small here and I have all these distances and I add them up really, really tiny, that's what this is doing. And this integral is sort of adding that up infinitesimally, and it's an infinite sum of infinitesimal quantities. So it's kind of a little more complicated, a little more advanced on how you do this, but you can still sort of see that there's a distance formula that's floating around here. In fact, if we look at this quantity a little bit more carefully, if I do sort of a formal computation here, now calculus students, don't scream at me. I'm going to do something a little bit here that's a bit heuristic. You know you're not really supposed to be able to do what I'm going to do, but it kind of shows you sort of where these formulas come from and how they kind of work together. What I'm going to do is I'm going to square this term and move them inside the square root and distribute it. And if you do this sort of formal computation where you sort of cheat a little bit, this here is a function, and so this is kind of a little bit of a cheat to think of it this way. It's not exactly true, but it's an interesting way to see this. If you pull this in here as if it were a number, you'd have something that looked like this. If you were to distribute this in here, you'd end up getting a formula that looks like this. Because the dt squared, when it hits this guy, will cancel with that dt squared. This one here will cancel with that one. And what you have here is something kind of interesting. This looks very similar to this formula up here. At one point, we could call this our delta x and this our delta y, which are changes in x and changes in y. And so you'd have delta x squared plus delta y squared, and it would look something like this. And that's remarkably similar to what's going on here. So at least formally, this is sort of picking that up. And you can kind of use this formal notation to help you understand sort of what's going on with this. Since these are infinitesimally thin quantities as opposed to these, which actually might have some substance to them, this is like an infinitesimal distance along that curve. So sometimes this quantity is referred to as ds, and then if you squared both sides here, you'd get ds squared is equal to dx squared plus dy squared, which really, if you look at that, is just the Pythagorean theorem. But this hidden inside of it is notationally keeping track of all of this stuff going on so that you can pick whatever parameterization you want. So for example, if you use this guy here, either one of these two, and you look at the two formulas we had for the arc length, this one here can be found by dividing a dt squared across both of these things here and factoring out a dt squared from the whole square root. This one here you can get from here by doing that same formal computation, but this time dividing by dx squared, and it ends up producing the same formula. So this is kind of a handy way to keep track of this in a shorthand kind of method. And this is usually referred to as a line element because it's telling you how to compute sort of an infinitesimal distance along a curve. So you could call this an infinitesimal Pythagorean theorem. This is where it gets kind of interesting because infinitesimal Pythagorean theorems tell us how to do a lot of things. For example, if you do a little bit of linear algebra, you'll learn that if you have a vector v, which is equal to x1, y1, if you compute the length of this vector squared, you know that you take x1 squared and add it to y1 squared. That's how we write length squared for a vector. But you also might know, if you took linear algebra, that you can rewrite this as the dot product of v with itself. So in a dot product, if v is equal to x1, y1, and u is equal to x2, y2, then when you do v dot u, you get this quantity where you multiply the x coordinates and add it to multiplying the y coordinates. You get x1, x2 plus y1, y2. Well, if x1 and x2 and y1 and y2 were the same numbers, respectively, then that results in this equation here. And so you can see that if you dot product v with itself, that's the formula you're going to get. You can go a step further. If you take the dot product of two vectors, you'll find that those are equal to the length of v, which is the square root of that, the square root of that, times the length of u, times the cosine of the angle between them. So what's interesting here is the following. You have a Pythagorean theorem-like thing here, which relates to a dot product-like thing here, and that dot product thing tells you something about angles. So this Pythagorean theorem kind of keeps track of lengths and angles in this way. What happens is, though, is sometimes this might not be the formula you want to use for the length. As we mentioned earlier, you can change kind of what you mean by length. And if you do that in certain circumstances, you can actually start describing some real stuff. This right here is this infinitesimal Pythagorean theorem, which corresponds to something that you compute lengths of vectors with, which corresponds to a dot product, which corresponds to how you compute angles. So it's sort of telling you how to do geometry in that space. And you can up this dimension a little bit. And we'll use this line element to sort of help us with this. So if you're in R2, you use this infinitesimal Pythagorean theorem. If you go up to R3, it actually turns out it's not too hard. It just sort of follows the same pattern. You get a dx squared plus a dy squared, only this time you also get a plus dz squared. And you can go one step further and go into R4. And why would you care about R4? Well, these are sort of spatial dimensions, but if you want to describe our universe, you need to talk about both space and time. You need a space-time. And that requires 4 coordinates for each position. The spatial position that it has, the x, y, z, and then also what time that's occurring. And we actually call a coordinate point in a space-time, we call it an event, because it has a location and a time, kind of like a party or something like that. So it's an event. But anyway, if you just naturally went forward, in R4, you'd have this ds squared equals dt squared plus dx squared plus dy squared plus dz squared. So back around the turn of the 20th century, Albert Einstein was trying to solve some really important physics problems. One of the problems that he was trying to solve was this issue with the Michelson-Morley experiment that showed that the speed of light was constant in every reference frame. That was something that didn't fit into Newtonian dynamics. It should have followed Newtonian relativity, but it didn't seem to be. There was also a bit of a problem with something called the perihelion of Mercury advancing a little too much from what should be predicted from Newtonian mechanics. And these questions were sort of plaguing the physics community in the late 19th century. Around the turn of the 20th century, Albert Einstein figured out how to solve the speed of light being constant in every reference frame. About 10 years later, he figured the other part out, but I want to focus on this first part here. So in 1905, he published a paper about special relativity. And in that paper, he described how space and time were really elements of the same thing and should be treated sort of the same, but that how we measured things were relative, including how we measured time. And it was really novel and kind of complicated. He used a little bit of hyperbolic trigonometry and a few other ideas there. And when he first described it, it was kind of in an algebraically kind of way. Well, around the same time on the math side, a branch of mathematics called differential geometry was being developed, which looked at things like these infinitesimal Pythagorean theorem and how it produces geometry about it. Well, one of Einstein's former math teachers, a guy named Hermann Minkowski, watched one of his lectures that he gave on special relativity, and Minkowski realized that what Einstein was describing could actually be described within that framework of differential geometry. He called this Minkowski space, we'll call it M4, and he said that you would start with maybe just the standard dt squared plus dx squared plus dy squared plus dz squared, but that you could resolve what Einstein was talking about by looking at the geometry that's induced not by this, but by putting a negative sign in front of the dt squared. So that's a little weird, but it kind of works the same way as what we had before. It's still using an infinitesimal Pythagorean theorem. And then you would use this to figure out what the corresponding dot product is and what the corresponding angle measures are and all that kind of stuff. And it turns out that the geometry that this induces is precisely the same geometry as what Einstein was describing in special relativity. So in a massless universe where you don't have any stars or anything, this is actually describes exactly how that universe would behave, including things like time dilation and length contraction. But it all comes down to this infinitesimal Pythagorean theorem. At first, Albert Einstein was kind of resistant to this idea, thought it was sort of mathematical nonsense and didn't really help. But as he was trying to solve the problem of including gravity into his model, he realized that this actually gave an insight to how you could think about that. And so over the next several years, he started working with mathematicians to learn the basic ideas behind Riemannian geometry, which is a branch of differential geometry that talks about this kind of stuff. And he was able to realize that you could incorporate gravity by allowing this equation, this infinitesimal Pythagorean theorem, to change dramatically. And if you allow sort of the coefficients to change and a whole bunch of other things like that, you can actually get a model that describes how things move in space and time. And that's essentially what he came up with general relativity, which basically takes the induced geometry here, which can be described using something called the Einstein curvature tensor, but it's this guy here, this capital G, is really built out of geometry that comes from an infinitesimal Pythagorean theorem, and that it would equal 8 pi times t, where t is this thing called a stress energy tensor, which sort of measures where matter is and how it moves. And he said that these two things being equal produces the geometry that we see when you have massive bodies in a space-time that kind of behaves a little like this. So there's some elements of Minkowski space, but you change this infinitesimal Pythagorean theorem, which they refer to as a metric or a line element, and it turns it into what the geometry would be here. And what's kind of neat is that that changes things like what lines are straight and all sorts of stuff like that. So you get gravity sort of for free because it ends up being just objects trying to follow the straightest possible curves in the geometry induced by this infinitesimal Pythagorean theorem. It's a little complicated to get into, and so I'm not really going to get into that too much. What I want to impress upon you here is how much the distance formula and the Pythagorean theorem influenced this conversation and how important it was. And it actually turns out that you have to take into account this kind of curved geometry that's induced by these infinitesimal Pythagorean theorems every time you do a GPS calculation, because the clocks that run on the GPS satellites run differently than the clocks on Earth because they're in a different location in this weird curvy warped geometry. And so they actually have to run the clocks a little slow on GPS satellite in order to make it stay synced with clocks on the Earth's surface. And the way they figure it out is by doing computations that are based in this infinitesimal Pythagorean theorem geometry. All of this stuff is basically coming out of using the Pythagorean theorem in a much more complicated, much more interesting and crazy space that allows us to understand the world around us a little bit more. So there's a ton of stuff that has to do with the distance formula and how it can help us understand and measure the world around us. That's it for our series on the distance formula. I hope you really enjoyed it. If you did, please hit that like button and subscribe to Scholar Sauce. If you're interested in learning a little bit more about that general relativity idea and how it relates to a distance formula, and you want to do it by seeing a lot of pictures, you can click here where I give a lecture introducing the basics of general relativity using nothing but pictures. Or if you'd like, you can see a more general content video from our channel over here. I really hope you enjoyed this series. If you did, please share it with your friends. We'd like to reach as many people as we can. We'll see you next time on Scholar Sauce.